In combined loading, there is one concept that is tricky. And that concept is using the right-hand rule in order to move the forces from one point to another point. And that requires a lot of visualization. So today I try my best to explain that concept, which requires visualizations. We have previously learned this concept in physics, also in statics. So that is not a new topic, but we want to practice that again, and we want to apply that for three-dimensional problems, which could be complex because it requires moving the forces in a three-dimensional space, and that requires, again, visualization. So I'm going to explain that using one example. There is a pipe that is subjected to three forces, and we want to determine how much are different stresses at point H, which is located close to the bottom support of this pipe. So in order to solve this problem, the very first step is moving all of these forces one by one to the section that is passing through point of interest. The very first move would be moving force Px by distance of A to this y-axis. We know that it is producing a moment because this force is moved perpendicular to its direction. But what kind of moment is that? And what direction that moment would be about? So I'm going to use my right hand along the direction of the force, and palm, as you can see on the animation, is going to be to the direction that we are moving the force. What is the direction of thumb? Is upward in the positive direction of y. What kind of moment that is? Let's see. This force, if acts on this side, it is going to twist the shaft, right? If the thumb is perpendicular to this cut section, it is twisting the elements. The magnitude of this torsion is going to be equal to Px multiplied by A. As you can see here, this is the torque that is produced at the bottom of the section. All right, the second move would be moving this force downward. In that case, if we move the force downward, we need to put again the hand along the direction of the force. So now hand is going to be again in that direction, but the palm is going to be downward because this is where the force is traveling. The moment produced by that is going to be equal to Px multiplied by the distance that the force has traveled, which is B. And the direction that the moment is acting on would be shown by the thumb. So in that case, as we can see, thumb is going to be along the negative direction of Z. So I'm going to form a table to simplify our calculation. We know that in general, at each section, we would have three forces and three moments. One of these forces would be axial force, the other two are going to be shear, and one of the moments would be torque, and the other are going to be bending. So speaking of force Px, which has the magnitude of 15 kilonewton, after moving the forces, we see one shear force, one torque, and one moment produced by this force. The torque, as we discussed, is going to be Px multiplied by A, and the moment about the Z is Px multiplied by B with the negative sign. And there will be a shear force with the magnitude of Px along the x direction. All other components are going to be zero because there is no other component, moment, or force produced by this one. Does that make sense? Okay, now let's move on and repeat the process for all other forces. It is going to be exactly the same as the one that we have done here. All right, now we are focusing on the force in the y direction. In that case, again, we have to move this force by distance of A to the y-axis, but the type of moment produced by this move would be different. Put the hand downward along the direction of the force and face palm toward the direction where you are moving the force. The bending moment would be about positive direction of x. So bending moment would be Py multiplied by A, and sign of that would be positive, okay? The second move would be moving this force downward. When I move this force downward, once this force arrives to that point, that would be an axial force because this force is perpendicular to the cut section area. On the other side, this move is not producing any extra moment because the force has traveled along its axial direction, right? This force is producing two components. One moment about x, the magnitude of that is Py multiplied by A, positive, and one axial force with the magnitude of Py, with negative sign. Why did I use negative sign here? Because the force is compressing the element. Moment above the x is going to be Py multiplied by A, positive, axial force is going to be negative Py, and all other components are going to be 0. All right? Now let's do that for the very last force, force Pz. Now we are getting rid of all other forces, and we just focus on Pz. The first move is not producing any extra moment because we are moving the force along its own direction. The second move, however, would produce extra moment. The magnitude of the moment would be equal to force multiplied by the distance, which is b, so that would be Pz multiplied by b, and the direction is determined using the right-hand rule. So again, we're going to put the force along the direction of Pz, face palm downward toward the direction we have moved the force, and as we can see here, thumb is going to be about the x direction positive. So it is producing a moment about the x direction, and once this force gets to this cut section, it is producing shear force again, because this force is going to be parallel to the cut section, right? So in this table, this force Pz is producing a shear force about the positive direction of z, and it is producing a moment about the positive direction of x with the magnitude of Pz multiplied by b, and all other components are going to be 0. If we want to put the effect of all of these three forces together, we need to add them up together. So starting from the very first one, there is only one force producing shear force in the x direction, and that comes from Px. So the total shear force in the x direction is positive 15 kilonewton. There is one force that is producing axial force in the y direction, and the magnitude would be negative 52 kilonewton, and shear force in the z direction would be positive 27 kilonewton. In the same way, there are two components that are producing moment. They are both positive, so I would add the values of these two. The result is 118.9 kilonewton meter. Torque about the y direction would be 19.5, and moment about the z direction is negative 28.5 kilonewton meter. So that is the very first step where we are using the right-hand rule in order to determine the resultant forces. All right, before doing any calculation, I think it would be good for us to do some calculation for section properties, because we are going to use them later on. The very first section property would be cross-section area. Area of the tube is simply pi over 4, external diameter squared minus internal diameter squared. And given the external and the wall thickness, I can determine the internal diameter, plug in the value, and calculate the area. Tube is symmetric, which means that moment of inertia about x and z are going to be the same. And that would be equal to pi over 64 multiplied by external diameter to the 4th minus internal diameter to the 4th, right? Okay, what about J value? We would need J for determining torsion. J is simply sum of the moment of inertia about x and z. So in two perpendicular directions, add them together. Or we can use the equation that we have previously learned, pi over 32, external diameter to the 4th minus internal diameter to the 4th. So all of these properties were calculated. Now we get to the tricky part, and that is the first moment of area, or Q. So pay attention to this part carefully, because that is typically a source of mistake for the calculation of shear stresses. Q depends on the point of interest and the axis of interest, as opposed to area, moment of inertia, or J, which are calculated for the entire section. Q is calculated for a particular point and for a particular axis. Point of interest for this problem is H, which is shown by red here. And I want to determine Q for that point once about the z direction and once about the x direction. Okay? Let's start doing that for z direction. How do we calculate Q? Again, remember what we have learned in Chapter 7 in shear stress in beams. In order to calculate Q, we are going to cut this section passing through the point of interest parallel to the axis of interest, which is Z. So I'm going to cut this pipe passing through point H parallel to the Z direction, like this. What area do we cut here? 0. Area is 0. That means Q is going to be 0. So Q, or the first moment of area, for point H about Z is 0. In a similar way, we can determine Q for point H about the x direction, which we call that Q sub x. In that case, we are going to cut this section parallel to the x-axis, passing through point H. We are cutting half of the section, which we know that is giving us the maximum Q, because Q is going to be maximum at the centroid of the section. So the Q maximum for a tubular section is 1/12 external diameter cubed minus internal diameter cubed. Now, after doing all of these calculations, we are ready to go and calculate stresses produced by each of these forces. The very first case would be considering stress produced by the axial force, the simplest equation that we have learned, and that would be simply force divided by area. It is producing uniformly distributed stress on the section, and the magnitude of that is F divided by A. That gives us stress. Carry the negative sign to make sure that this is showing the compressive stress. Now we talk about the bending. Bending, again, could be tricky, and that requires visualization. Let's start with bending stress due to mx. When we talk about mx, note that moment about the x-axis was positive. What does it mean? It means that I need to put my thumb along the positive direction of x. Stress distribution on the section is going to be calculated from this equation, mc divided by I, and this is going to be the distribution of stress. So I showed this moment with a double arrow, which is the direction of the thumb, and based on that, we can see that stress at point H is basically 0, because that point is passing through the centroid of the section with respect to the x-axis. Remember that bending stress is going to be linearly variable. It would be 0 at the centroid, and it would be maximum once we get to the farthest distance from the centroid. Okay? Now we talk about the last bending moment, which is moment about the z direction. Stress distribution on the section is going to be like this. We see the maximum stress at point H. Is it compressive or tensile? It is compressive. How do we know that? Again, using the right-hand rule. We put the thumb along the direction of moment, curl the finger, we can see that at that point, the beam is being compressed. This stress would get negative sign. The magnitude of that would be calculated from this equation, mc divided by I. I'm using subscript of z. So moment is about z, moment of inertia about z, and distance is also measured from the z direction. When we are talking about the moment about x, everything gets subscript of x. All are calculated from the x direction. All right, I'm going to plug in the value of moment, I and the c. Remember that I will not carry over the sign of moment because I have already determined the sign based on the direction of the moment acting on a section. The total bending stress at that point would be equal to negative 109 megapascal. All right. How much would be the total normal stress at that point? Total stress is sum of the axial stress plus the bending stress about the x and z direction. So adding the values results in 119 megapascal compressive. All right. Now we are going to calculate shear, which is more tricky. So there are 3 forces that are producing shear. Shear force in the x direction, shear force in the z direction, and torsion. All right? So let's start with determining shear stress due to shear force Vx. We know that shear stress equation is Vq divided by IT, but pay attention to the subscripts. When you want to calculate shear stress produced by Vx, Vx belongs to the z family, so everything gets subscript of z except the shear force. So we have V sub x multiplied by Q sub z, I sub z, and the thickness is calculated also for the z direction. Q for z direction was 0. We calculated that before, and that means that shear stress produced by that is going to be 0. If I want to draw that stress distribution on the section, we can also conclude that visually here. If we look at this section from top view, the point of interest is located on bottom, where the shear force is in a vertical direction. That point would have the farthest distance from the centroid, and we have already remembered that in shearing beams, that point would get 0 stress because Q would be 0 for that point. Q is maximum at the centroid. So if our point were located over here or here, it would have the maximum stress. All right, Now let's calculate stress produced by V sub Z. Shear stress is again calculated from VQ over IT equation. VZ belongs to the X family. So we have a V sub Z multiplied by QX divided by IX divided by thickness. QX was calculated previously. IX was also calculated. And I'm just going to plug in the values here and determine the magnitude of shear stress produced by this force. We can also show the distribution of stress on this section. Now in that case, VZ is going to be in the horizontal direction if you look at the section from top view. Now point of interest H, which is shown in red, would have the maximum stress because this is located on the neutral axis. We are not done yet because we need to also consider stresses produced by torque. So torque is also producing shear stress, and the magnitude of that is calculated from this equation, TC divided by J. Torque was calculated, J was calculated, C is the distance of the point from the centroid, which is simply half of the external diameter. But we need to pay attention to the direction of stress. So remember, torque was positive. It means that put the thumb along the positive direction of Y. Curl the finger. If you look at that from top view, the element is twisting counterclockwise, right? So for the point located on the bottom of section, for this red point, what would be the direction of stress? Going to the left or going to the right? It is going to the right side. This one is opposite to the direction of stress that was produced by VZ. This is the way we determine sign. We do not determine sign based on the sign of shear force or sign of moment. We look into that based on how they are applied, and then we are going to determine sign later on the stress elements. But I'm going to show that in a little bit later. Okay, first let's calculate the magnitude of the stress. Torque was 19.5. Convert that into Newton millimeter multiplied by C, which is half of external diameter, divided by J, and we get stress. We know that these two stresses produced by torque and VZ are going to be opposite to each other. So the total shear stress is going to be the difference between these two. Which of these two is dominant? Stress produced by torsion is dominant, so the total resultant stress, if you look at that section from top, is going to the right side. The magnitude of that is going to be 26.8 megapascal. Okay, I know that it was a long problem, but this is probably the most confusing part of this problem. How do we determine sign of shear stress? In order to determine sign of shear stress, we do not take sign from the sign of torque or sign of shear force. We have to draw stress element. Focus on this three-dimensional stress element, take it out, and draw all stresses distributing on that section. And I can make a two-dimensional stress element out of that by looking at this section from this x-axis. In that case, we just see the green surface, and we would be able to draw stress elements. The axial stress was compressive. The magnitude of that was negative 119 megapascal. Okay? So sign for axial stress was determined based on whether the element is compressed or under tension. For determining shear stress sign, we need to see what is the direction of stress. We have already noticed that stress on the top surface, on the red surface, is dominant by the torsion. It's going to be to the right. So I'm going to draw that here. If I do that, we know that same stress or consistent stress should exist on the other surfaces. So if stress on the top surface is to the right, we have to have tail to tail and head to head, and this is going to be stress distribution on the section. Now, is this stress positive or negative? Remember, in order to determine sign of shear stress, we look at the right surface. If stress is upward, it's positive. If it's downward, it is negative. So sign of shear stress here is going to be positive. And that would give us the state of stress for this section. So if you understand this concept for one problem, then you would master the concept and you can apply that for every other problem. We do not want to memorize the problems. We want to understand how these concepts could be used for solving different cases. Now I'm going to wrap up our discussion today with looking into how this concept could be used for the sections that are non-symmetric. So this section that we talked about was symmetric. It was a tubular section. The moment of inertia about every direction was the same. Now I'm going to apply this concept to a non-symmetric section. So in this problem, we are working with a section with a rectangular cross-section area, which is subjected to three forces, Px, Py, and Pz. And these forces are acting at different points along the beam. And I'm interested in determining stresses at K. I'm going to use the same concept without numerical calculation, but looking into that conceptually. First of all, I'm going to move force Px, so I'm going to get rid of the others. We are going to cut this section passing through point K and move force Px to the centroid of that section. Remember, we don't move the force to point of interest. We move the force to the centroid of the section. The first move would be moving the force along its own axis, which is not producing any moment. The second move would be moving the force perpendicular to its direction, so there will be a bending moment. This moment would be equal to the distance that the force has traveled multiplied by the magnitude of the force. The direction of the moment using the right-hand rule, as we can see, is going to be positive y, so moment about the y direction. Once this force gets here, it is producing shear force because this force is parallel to the section. Okay, now let's see what kind of stresses are expected to happen. I'm going to focus on the bending. How the beam is bending in this case. The axis of interest is y. So every point along the y direction on that section would have zero stress. And once I get away from that, stress is going to linearly increase. So as we can see, based on the direction of the moment, point K is going to be compressed. So it is going to get negative sign. Again, I can't emphasize how important is this. We do not take sign from the moment. We use the right-hand rule to see how the element is bending and what kind of stress is produced because of that bending. So stress at this point is going to be negative or compressive. That was for bending moment. What about shear? Shear is going to be opposite. So we can see here that bending stress is zero here, maximum on the sides. Shear is going to be opposite. It is going to be maximum at the centroid, zero on the sides. The magnitude of shear stress could be calculated using VQ divided by IT. Remember, Q is calculated by cutting the section parallel to the y direction, passing through point of K, and then we can calculate how much is Q and how much is stress. Okay, the next one would be calculating the force Py, and we're going to do the exact same process. So in this one, we are going to move force Py. The first move would not cause any moment. The second one is producing a moment, and that moment is about the x direction. And this force is shear because the force is parallel to the section. And bending stress, again, would be compressive, maximum at point K, because this force is at the farthest distance from the centroid. And shear stress would be zero for that point, because now this point is on the farthest distance from the centroid, resulting in zero stress. Okay? All right, the last one is force Pz, which is going to move along its own direction. This force is not producing any moment because this is just moving along its own direction. Once this force gets there, it is going to be an axial force, tensile, and stress is going to be uniformly distributed on a section. So I would determine three normal stresses produced by axial force, moment about the x, moment about y, and I would determine shear stresses produced by Vx and Vy, and then make up the stress element in a three-dimensional way, and then calculate stresses at that point. So again, I wanted to show you some animations. Hopefully, we can understand this concept in one or two problems. An exact same process could be used for every other single problem. This is going to be a complex topic, but this is not new. It just requires visualization. All right, thank you very much. I typically don't speak that much, but I'm hoping that it was useful for learning the concept. And we're going to practice this concept more on Friday. We're going to solve more complex problems.